Welcome back. This is marginal distribution part 2. And just a few minutes ago, we completed this table that you see right here. And this table is the joint probability distribution for a weighted coin and a weighted die. And you've watched part 1, I hope, and so you remember what those things are. Now, how would we use that table? If we were asked to find the probability of something like die equal 3, coin equal heads, we can use the table by finding where is the die equal to 3, right here. Where is the coin equal to heads, down here. And this intersection is the probability that the die equal 3 and the coin equal heads, 12 over 64, and that would reduce to 3 over 16. One more, the probability of the die is less than 3 and the coin equal tails. Well, if the die is less than 3 and the coin is equal to tails, we would be talking about die being less than 3, means it has to either be 2 or 1. And the coin is equal to tails, so we'd be talking about this probability or that one. So this would be equal to 2 over 64 plus, right under it, 3 over 64 equal 5 over 64, and I don't believe that one will reduce. All right, so that's a table that serves as the joint probability function. But more often we'll have a probability function that'll be serving for the joint PDF. So let's take a look at how that would work. So let's let x, y be discrete random variables. F of x, y equals the probability that x is equal to x, y is equal to y, is called a joint probability distribution of x, y. Now, your author doesn't do this, but many authors would talk about this, since it's discrete, as being a probability mass function. And I kind of have got used to that terminology, so if I say probability mass function, you know what I'm talking about. If this is in fact a probability mass function, it's got two properties. It has to have two properties. F of x, y has got to be greater than or equal to 0 for all x, for all y. And if I sum over all the x's and sum over all the y's, f of x, y, I've got to get 1. Now, we just saw that the probability mass function defined by that table for the coin and the die satisfied this property, and all the entries were positive. It satisfied this property as well. There are cases that are maybe just a tiny bit more challenging and therefore more interesting. And shall we get a clean piece of paper? All right, here's a clean piece of paper. Let's look at problem 3.62 from page 103 3. And this says that f of x comma y comma z is equal to k x times y times z. And x is allowed to take the values 1 and 2. Y is allowed to take the values 1, 2, 3. Z can take the values 1, 2. And we have to find the value of k so that f of x, y, z is a probability mass function for random variables x, y, z. So we looked at the definition for x and y, and now we're just jumping ahead and throwing in a third variable. Not much changes, and this would be, let me see if I can think of what this might be. Maybe we're looking to sample a person, and x is equal to the number of children that person has, y is equal to the number of cars that that person owns, and z is equal to whatever you want z to be, the number of the number of computers in the house. Okay, so there's 3 variables, x, y, and z. But what it is not important for this problem. We've got to find the value of k that will make this a probability mass function. And so the first thing that would have to be true for the probability mass function is that for all values of x, y, and z, this quantity has got to be non-negative. This guy has got to be non-negative. Well, it's the product of 3 numbers, x, y, z, and they're all positive integers, so no problem there. But that tells me that k is going to have to be positive also. If k were negative, then this would be negative, no go, because we've got to have f of x, y, z greater than 0. So we know that k has got to be greater than 0. And what else do we know? Well, we know that 1 is equal to sum over z, sum over y, it doesn't matter the order you put these in, sum over x of the f of x, y, z. And I don't want to have to write that twice, and so instead of writing the f of x, y, z, I'm going to skip right away to what that is, x times y times z. Now, what would that be equal to? Well, I might as well just index with the x, y, and z. So x, if I summed over x, x would go from 1 to 2, and I'm just referencing up here, and y would go from 1 to 3, and z would go from 1 to 2. Now, I'm going to do some algebraic manipulation before I add anything up. Now, k is not involved in the indexing here. K is a constant, and x goes from 1 to 2, but k just stays k. So k can come outside that summation. And that would put it in front of the y summation, but the same can be said. As y changes, k stays k. So move it out. And as z changes, k stays k, so move it out. So I'm going to have k outside of all of these. And all I have left here is x and y and z. Now we'll put the indices on in just a minute, but I want to make this argument again for you. As x goes from 1 to, what does x go to? 1 to 2. The y and the z don't change. For the purposes of this summation, the y and the z are constant. So they can come out, and I can have a yz here. And if I take them out, then I don't have them here anymore. Now when I look over here, this is y equal 1 to 3, and z doesn't play a role in that. Z doesn't change. It's a constant, so it can come outside the summation. And this is a z equal 1 to 2, so z takes part in this summation. Z can't move from there. Now, this is left over. Was my eraser. It was writing. Isn't that strange? All right, that's cleaned up. That looks better. And I moved this z out, so that's better. Now what do I have? I've got a k. Now I'm going to start over here with the x. This is x equal 1 to 2. That's the sum of the first two integers. You could just say 1 plus 2. Or you could say, okay, I recognize that series as a finite series, sum of the first two integers, which would be equal to 2 times 3 over 2. Formula for the sum of integers. And then let's move over here. This would be the sum of the first three integers, so that would be 3 times 4 over 2. And finally, this would be the sum of the first two integers, and that would be 2 times 3 over 2. Now I kind of got those out of order, but they're multiplication, and multiplication is commutative, and so I can be forgiven. 1 is equal to, let's do some arithmetic here, k, and this would be 3, and this would be 6, and this would be 3, so 3 times 3 would be 9, times 6 would be 54, 54k, or k is equal to 1 over 54. So we'd have to let k be 1 over 54 in this definition of the function, and then we would have a proper joint probability mass function for x and y and z. Now if we were to use this function up here with k equal to 1 over 54, this is problem 63 in that same set. And it asks us for things like, what's the probability that x is equal to 1 and y is less than or equal to 2 and z is equal to 1. So this would be, I'll do it this way. The probability, let's keep these in the order x, y, z. So this would be 1, 1, 1, or 1, 2, 1. Now what does that mean? This condition is x equal 1, y equal 1, z equals 1. It'd also be satisfied by x equal 1, y equal 2, z equal 1. So that's the or that I've got in here. Now these are disjoint, so the probability of the or would be the sum of their probabilities. And we can calculate this probability because we know the probability mass function is, now the k is 1 over 54 we discovered. So it would be 1 times 1 times 1 over 54 plus 1 times 2 times 1 over 54 is equal to 3 over 54 is equal to 1 over 18. And now we've gone 15 minutes, so we're going to break again. We'll finish this up in the next video.